Okay, so here's the solution to quiz 3. So number 1, I made this term up, it doesn't exist. ICAP is internal configuration access port. It's essentially used to instantiate a JTAG controller on the FPGA. It's part of its hard IP. DCM is digital clock management. And then phase lock loop, PLL. PLL, if you said something like it can increase and decrease frequencies, it's fine. Digital clock management, you could have said the same thing. Increase, reduce clock frequencies. Both of them, you could have also said something along the lines of move the phase of the clock, right? So if the original clock is like this, move the phase off a little bit for a phase offset. Name one logic conversion method I mentioned in the video. You had banking, IC, and then you also had a voltage divider. For banking, you're essentially sending, the FPGA has different banks, B0, B1, B0 and B1. B0 could be connected to 3.3 volts. B1 could be connected to 1.2 volts. You can instantiate a buffer inside the FPGA fabric to communicate between B0 and B1. The FPGA, the device on this side and this side can talk through the FPGA, or the FPGA can talk to them individually at different voltages if we have different banks. The next one is IC, integrated circuit. You just use a specific voltage divider chip. Okay. The last one is a voltage divider, where you have a resistor here, input voltage, out. So a system here has a higher voltage, maybe it's a 5-volt system. Over here it is a 3.3 volt system. You essentially use a voltage divider. You go from 5 volts to 3.3. If you set the voltage divider up correctly with R1 and R2, you can get essentially when it's 5 volts out, from this side, you can voltage divide it down to 3.3, so the system sees 3.3 volts on this side. This is a 3.3 volt system. And then the other thing is when this logic level is 0 on the side, if it's logic level 0, 0 is going to come here, 0 volts, come here, it's also ground, 0 volts. The output's going to see 0 volts as well, okay? So equations R2 over R1 plus R2 times V in equals V out. You didn't need to put that. You wouldn't have had to put that. Just had just described that you're using the voltage divider to reduce the voltage from system A to system B, and that when we see 5 volts here, we can reduce it to 3.3, so it's the same level. And when we see a 0 or a logic level 0, we see 0 volts here. 0 volts here and 0 volts here means that you'll see a 0 on the output, which means it'll still see logic level 1 and 0. The next question is the internal logic diagram, essentially a 7-segment. So is this a common anode or cathode display? Okay, so I've drawn it numerous times. It goes anode, cathode, the line is a cathode, so all the cathodes are hooked up together, so it's a common cathode display. Okay, you have to use persistence of vision in order to describe, drive the display. What does persistence of vision mean? It means that we're changing the digits so quickly that your eyes can't tell the difference, right? We're quickly lighting digit 1, then turning digit 1 off, quickly lighting digit 2, and then turning it off. So you do that at a level above persistence of vision, and you essentially see 2 values at the same time. So the frequency at which persistence of vision works is anything higher than probably, let's say, 60 hertz, 120 hertz. Anything higher than that, I'll take. So persistence of vision, again, means that you're switching it at a high enough rate, the display at a high enough rate where you can't tell the difference. The object looks like it's changing to you at the same time, but it's really not. It's just being driven past the refresh rate that you can see. Let's see. And then number 7, given this 2-digit 7-segment display, describe and provide pseudocode on how to drive it so that numbers 1 and 5 show up at the same time. So, how do we light number 1 and 5, right? 1 would be this, 5 would be this. So for 5, we would need to light segment, let's see, A. A is connected to 7. F is connected to 10. G is connected to 4, pin 4. This one right here is connected to C, so C is over here, connected to pin 2. These need to be on, and the rest of them need to be off to show a 5. This one, B and C need to be on, so B and C are connected to 3 and 2 need to be on. The rest of them need to be off. Then, the next step, after sending a 1 and a 5 to each display, you can't send a 1 and 5 at the same time. So you're going to send 1, set pin 9 to 0 to ground, and pin 6 to 1. So disable essentially digit 2, enable digit 1, because high potential to low potential. We're setting it to 0 volts, or logic 0 for digit 1, which means that 1 will turn on. Then we're going to set digit 1 back to 1 to turn off, and then digit 2 gets set to 0, and then we send the 5 equivalent to the pins. Right? So essentially, swapping between digit 1 and digit 0 involves pin 9 and pin 6. So set pin 9, or what is this? I don't remember what that pin was. Pin 9 and pin 6. So the first step is to essentially set these pins over here to 3 and 2 only on for the 1. Set digit 1 to 0, pin 9 to 0, so that pin, essentially segment C and, oh, wait, did I get that wrong? That's C and D, that's B. Sorry, that's B, so that should be 8. That should be pin 8 and 3, not 3 and 2. Okay, so set pin 3 and 8 to high, set pin 9 to 0 to get the 1 to show up on the digit 1. Then set this back to 1 to turn digit 1 off. Set digit 2 to 0, pin 6 to 0, and feed in the appropriate value for the 5, right? In this case, it's 71042. 71042. So C is, oh, pin 3, sorry. Let's just go over that again. That's an A, which is pin 7. That is a F, which is pin 10. This is a G, which is pin 4. This is a C, which is pin 3. And then this is a C, which is a pin 3. And then the last one would be this D, which is pin 2. So these segments would need to be set to 1, logic level 1. Okay?